to the next session chair, Xiaofeng.
Hello, can you hear me?
Yes, we can.
Okay, great. All right, next is our first regular session. Our first speaker is Kevin Liu from Ohio State University, and his talk is about computing networking algorithm co-design for decentralized learning over wireless computing networks. Kevin is an assistant professor in the Department of ECE at the Ohio State University, and he was with Iowa State University, and his research area include theoretical machine learning, control and optimization for stochastic networks, and optimization for data analytics in infrastructure and cyber physical systems. So to save time, let's give the stage to Dr. Liu.
Hello everyone. Good morning. Thanks for the introduction, Zafeng. So first of all, let me try to share my screen. Okay. Oops. Can you see the slides? Obviously.
Yes, we can see them.
Okay, good. All right. So yeah, I'm not very familiar with Webex. So all right. So good morning, everyone again. So my name is Kevin Liu. I'm working in the Department of Electrical and Computer Engineering at Ohio State. So today I'm going to talk about computing networking co-design for decentralized learning over wireless computing networks. Okay. So basically, the need for decentralized learning over networks arises in many different applications, including many traditional wireless networking optimization problems, and also in many data center distributed machine learning, and many new multi-agent systems, and even including some smart electric power grid problems. Okay, so basically here's a very quick overview of decentralized learning, which is also known as network consensus optimization. So basically we have a network represented by a graph, which has n nodes and out links. And all the nodes are trying to optimize the same global some state or decision variable, and each node can only access some local objective function, but not the global objective function. Okay, and the global objective function is basically the sum of all these local objective functions. So the goal is trying to solve this problem distributively and in a collaborative fashion. So clearly, this problem can be equivalently if reformulated into the following consensus form, where we introduce some local copy called xi at each node I, such that each xi equal to xj if node I and node j are connected in the network. Okay, so clearly these two problems are having the same solution. So here's just one very easy and maybe a concrete example. So consider a tactical multi-agent systems, which can consist of drones, robots, or soldiers on the ground. So each agent is trying to collect some data, for example, some images, and the whole system is just trying to do some image regression problem. But because of the security or privacy concerns, the agents cannot transmit all the data to a centralized location, so they have to do it in a distributed fashion. So, for example, the images can be represented by the following, parameters, such as the pixels, the geographical locations, the ground truth label, so on and so forth. Okay, and then the agents are trying to learn some linear model parameters called X. Okay, and then it can be easily shown that this problem can be written as the following form, with if each f of x is written in the following format. Okay, so this is exactly fitting our formal formulation. So in fact, to solve this kind of problem, it has been well known that this decentralized gradient descent method is pretty effective. So basically, the idea here is to reformulate this problem, okay, in the following form, which is proposed by Nedick and Oxtagler in more than a decade ago. So here, we will introduce a notion called consensus matrix W. So this W will satisfy it's basically a matrix of weight parameters, and then it satisfies the following properties. First of all, it's doubly stochastic, meaning that all rows sum to 1, all columns sum to 1 in this matrix. And then this matrix follows the same network topology sparsity as the underlying network topology. Okay, so basically, if you have an edge between node I and node j, then the corresponding entry in this matrix will be non-zero, positive actually. Otherwise, it's 0. Okay, and then this matrix is clearly symmetric, and because of that, we have all real eigenvalues between this -1 to 1. Okay, and then they can be sorted. And here we would denote the second largest eigenvalue in magnitude, beta. Okay, so this will become an important parameter in our algorithm design. So basically, for example, for this kind of toy example, 4-node network, one of the W's can be written as the following form. Okay? Of course, the choice is not unique. So in this standard DGD algorithm, basically what we're doing is the following. So first of all, we choose some some initial values for the local variables and step size. And then in each iteration or communication round, each node just sends the local copy to the neighbors. Okay, and then upon receiving the local copies from its neighbors, each node will update its own local copy in the following fashion, which can be decomposed into 2 steps. This step is usually called consensus step, basically just a weighted average of your local copies, okay, from the neighbors. And then you'd also take the one gradient step, but this is a local gradient step because every node only knows its own local object function. So by doing this, it can be shown that as time goes on, this would converge. These local copies will converge to the overall network average, and also the network average will converge to the optimal solution under suitable assumptions and conditions. Okay, so this is the algorithm. So you can see that this algorithm has some very nice features. It's very easy to implement, and it also has very elegant network interpretation. And it can be also shown that it has a pretty fast convergence speed. Okay, it's actually same as the traditional gradient descent, but it's also problematic, and particularly in nowadays, if you perform this kind of deep learning over a large network. Okay, and particularly in wireless network where the communication links are not that reliable and oftentimes low speed. Okay, then this could become a big problem because the communication cost would be pretty high, and the communication would be very time consuming. Okay, so one example would be to carry out learning over satellite networks. So for example, in each kind of these kind of RF-based satellite network, the image usually of this kind of a typical resolution. And also the RF link usually is not that fast. This is also a pretty typical link speed. So so for this kind of network, the communication would be pretty inefficient. Okay, so one way to handle this kind of problem is to do a compression. Okay, basically we compress the information we are exchanging. However, it's not that difficult to see that the original DGD method with a straightforward compression is not going to work. Okay, so this is because if you directly exchange the compressed information, then it is pretty easy to show that you will always have some accumulated noise term in the information you're exchanging, which is not going to be killed over time, and then eventually this noise would kind of destroy your the convergence of your algorithm. Okay, so in the literature, people have come up with several different techniques to handle this kind of problem in doing compression while trying to make the original DGD method work. Okay? So these are some of the typical algorithms in the literature. Obviously, it's not comprehensive. So basically, in the literature, there are several different ideas. Either using uncoded DGD, meaning that you just exchange the DGD, doing the same kind of exchange as in the original DGD, with some kind of so-called noise power constraint compressors. Okay, so here, if you do that, of course you can, you need to modify the algorithm, but the convergence speed would be pretty slow. Okay, so on the other hand, there are some other people, including ourselves, which would try to modify the algorithm to exchange the differential information between the nodes rather than the X copy itself. So here the algorithm is also working under noise power constraint compressors. But again, these algorithms all have some implementation issues. So yeah, due to time limitation, I won't go into detail. So in this work, we are actually looking from a new angle. So again, we're doing some differential coded DGD, but here we look at like the more general SNR constraint compressors. Okay, and so there's another independent work compared to our work when we're working on this topic, but still we show that our work has a much higher SNR tolerance compared to this existing work, meaning that our algorithm can work with more aggressive compression, and which is more communication efficient. Okay. So basically in here, SNR constraints compressors is defined as the following. So if you have a compressor C, okay, and then compressing some information X, then you can decompose into the original message and some noise. Okay, so here the noise is assumed to be unbiased and satisfy this condition. Here, this eta is basically the SNR threshold. Okay, so the smaller the SNR threshold, the more aggressive your compression scheme is. Okay, so any scheme that satisfies these two conditions would be called SNR constraint, stochastic unbiased compressor. So two examples are the following. So one is the a pretty well-known sparsify operator, which satisfies this condition. Another also pretty well-known compressor is this ternary compressor, okay, which also satisfies this condition. And in comparison, the ternary compressor would be much more aggressive compared to sparsify. Okay. So here this is our proposed algorithm, which looks pretty similar to DGD, but also have some major differences. So here, the major difference is that we will introduce some auxiliary variable called y. Okay, and then in each iteration, each node will send the differential coded compressed information. We compress the differential between two consecutive iterations. Okay? And then upon receiving the information from each node, from the neighbors of each node, then each node would do the following calculation. Okay, so basically we update the X using this compressed information, do this kind of inexact update, and then we do a weighted local average on Y instead of X. Okay, and then we compute this local gradient update, and then we update the local differential, and then we repeat the whole process again. Okay, so it looks a little more complicated, but if you write it out in the following way. So first of all, if you consider this kind of Lyapunov function, which is basically the original fx plus some quadratic regularization term carrying this weighted this weight matrix, consensus matrix, then we can rewrite our updates in the following matrix and vector form. Okay, again, still looks pretty complicated, but after some algebraic derivation, we can show that the update direction, this differential, this d, okay, is basically the the negative gradient of this Lyapunov function. So why is this nice? Because you can see that our algorithm can be essentially viewed as some SGD method for solving this Lyapunov function. Okay, and then we can show that thanks to this SNR constraint compressor, we have this property, right? This unbiased property and also this noise property. Okay, and also if this algorithm converge, well, which of course needs to be shown, then then the gradient has to go to 0, which implies that from this condition, it implies that the noise from the compressor will also goes to 0. Okay, so this means that we don't have to modify the algorithm that much to tame the compression power, compression noise power in the information exchange. Okay, so now still we need to show this algorithm is converging. So to prove that, we first show that the following lemma. So if this function is Lipschitz, the step size satisfy these conditions, okay, and also the SNR threshold is not lower bounded as the following, then we can show this kind of condition on the Lyapunov function. Okay, so it's pretty technical. So let me just say the following. So as this network gets sparser and sparser, and also if this SNR lower bound is shrinking, then we can adopt this kind of compressor with a large compressor ratio. Okay, so meaning that when the network gets sparser and sparser, we can tolerate more and more aggressive compression. Okay, which is a nice thing. And then we based on the previous result, we show that if the function is smooth enough, okay, and the same step size adopted from the previous lemma, then we can show that each local copy will be converging to the average, okay, in the following way, all right? And then basically this is some noise pool, and this is a term. Right, and actually from the previous result, we can show that this term is bounded, and therefore this term is a vanishing term. Okay, so eventually we can show that the whole thing is converging to at least some finite error ball. Okay, and then we further show that this average, this mean, okay, the mean is also converging to some some stationary point. Okay, so again, this is some fixed error ball determined by the network topology, the second largest eigenvalue, plus a vanishing term. Okay, so this is pretty nice. So yeah. Furthermore, so if we adopt some vanishing step size instead of a constant step size. So previously we actually adopted a constant step size. But if the step size is vanishing, then we can show that by adopting this kind of a step size choices, we can get this kind of convergence rate result plus another vanishing term. Okay, so so basically this convergence rate would match the theoretical lower bound. So meaning that the convergence rate in here is actually optimal. Okay. So so earlier I talked about two types of controller, right? One is specifier, and another one is ternary. So they both have pros and cons. So this one, the specifier, has controllable SNR. You can control the SNR pretty easily, but the compression ratio is not very large. Okay. On the other hand, the ternary has a very nice compression ratio, meaning that it's more efficient, but it's hard to control the SNR. Okay. So based on this, actually, we want to achieve the best of both worlds. So we actually propose a hybrid compression in the following way. So so basically in here, given any high dimensional vector z, okay, for example, you can think of this as a large deep learning model being learned. Then we kind of use k so-called anchor elements, okay, and divide this vector into some groups. Okay, so so in here, in the first couple of groups, we will use this aggressive ternary compression, and for the last group, we use this the milder sparsify compression. Okay, so basically the idea is trying to achieve the best of both worlds, and of course in here, how to select this anchor point becomes another optimization problem. Unfortunately, this problem is a pretty difficult anti-hop problem. So in the end, we propose some greedy solution, greedy strategy to solve this problem efficiently. Okay, so now let me quickly show some numerical examples. So here we adopt the following network topology. This one is a little sparser. This one's a little denser. Okay, so these are all from the some real world data set, and then so we run our algorithm, and then you can see that with this is the convergence with respect to iterations. Okay, so you can see in here our algorithm with this hybrid compressor converged the most efficiently. Okay, so the fastest. The same thing also holds for the denser network. Okay, so you can see this our DCDGD plus this hybrid compressor will converges the fastest. Okay, so in terms of this convergence with respect to communication cost, so for the sparser network, you can see that our algorithm with this ternary is the most efficient. This is because ternary is pretty aggressive in the compression ratio. Right? However, in the denser network, you can see that the ternary actually diverged after a while. This is because in here the compression is too aggressive, too noisy. But on the other hand, our DC-DGD coupled with our proposed hybrid compression is still enjoying the fastest convergence speed. Okay, so this is shows that this hybrid compressor is pretty robust. All right, so to conclude, here in this work, we developed an algorithm called DC-DGD to reduce the communication costs for learning over networks, and particularly for pretty noisy but not reliable wireless networks. We show that this algorithm has a pretty fast convergence speed and also have low complexity algorithmically as the original DGD. And what's nicer is that we don't need to modify the original DGD that much, thanks to the adoption of this kind of a SNR constrained compressor, which enjoys this kind of self-compression noise reduction effect. Okay, so so this concludes my talk, and any questions is appreciated.
Okay, we have time for a quick question. Maybe I can just ask a very simple question. So your convergence result is in terms of the gradient norm. So are we looking at a non-convex problem?
Yes, we are talking about non-convex problem. Yeah, if the problem is convex, then we can say a little more. But here, we only evaluate the gradient.
Okay, great.
Gradient norm.